Welcome back to Clinical Hematology Reviews. Today, we'll be discussing monocytes and platelets. Monocytes typically constitute about 2 to 10% of total peripheral blood leukocytes in normal adults. Their primary physiological responsibility is executing host defense, which occurs once they migrate out of the vascular system and transform into tissue macrophages.
That tissue transformation represents the culmination of a distinct myeloid maturation pathway. Morphologically, we recognize three distinct stages along this lineage: the monoblast, the promonocyte, and the fully mature monocyte. Understanding how these stages evolve is critical for differentiating normal developmental forms from pathological conditions in the clinical laboratory.
Let's break down the earliest recognizable precursor, the monoblast. Measuring 12 to 20 micrometers in diameter, the monoblast maintains a very high nuclear to cytoplasmic ratio. Its nucleus is typically round or ovoid, though you might occasionally observe early indentation or subtle nuclear folding.
Under right Giemsa stain, the nuclear chromatin appears pale blue-purple, fine, dispersed, and distinctly lacy. Compared to myeloblasts, monoblasts display a relatively more abundant rim of cytoplasm. This cytoplasm is uniformly agranular and exhibits a characteristic blue-gray hue. Cytochemically, these blasts stain strongly positive for nonspecific esterase and express surface markers like CD14.
As the cell advances to the pro-monocyte stage, it maintains a size range of 12 to 20 micrometers, but the nucleus undergoes significant structural changes. The nuclear outline becomes noticeably irregular, displaying prominent indentations, creases, or deep folds.
The chromatin structure begins to transition from the delicate, lacy appearance of the blast toward a moderately coarse, woven pattern. While the cytoplasm retains its abundant blue-gray color, you may start seeing fine, azurophilic granules dispersed throughout. A key clinical laboratory takeaway is that immature forms like monoblasts and promonocytes are often categorized broadly as blast equivalents when performing differential counts in acute leukemia workups.
When the cell reaches full maturity in the blood, the monocyte presents a classic morphological profile. It remains 12 to 20 micrometers in diameter, featuring a distinctive horseshoe or kidney bean-shaped nucleus with extensive lobulations and delicate nuclear folds.
Its chromatin pattern is loose, linear, and remarkably lacy, which helps distinguish it from the dense, clumped chromatin of band neutrophils. The cytoplasm maintains its signature blue-gray appearance, filled with dust-like azurophilic granules that create a classic ground glass texture. Additionally, small cytoplasmic vacuoles are frequently observed even under completely normal, non-pathological conditions.
Monocytes do not perform their principal host defense duties within the blood vessel itself. Instead, they circulate briefly before undergoing diapedesis across the vascular endothelium into peripheral tissues. Once in the tissue microenvironment, they enlarge significantly, swelling to a diameter between 15 and 80 micrometers as they differentiate into mature macrophages.
Depending on the specific anatomical tissue they inhabit, these macrophages receive specialized names. In general connective tissue, we refer to them as histiocytes, while in the liver sinusoid, they are called Kupffer cells. In the pulmonary alveoli, they are alveolar macrophages. In the epidermis of the skin, they are Langerhans cells, and within the central nervous system, they function as microglial cells.
Looking at peripheral kinetics, monocytes remain in the circulation for approximately 8 hours before undergoing diapedesis into tissue spaces. Within the blood vessels, they're partitioned into two functional pools, the freely circulating pool and the marginating pool. The marginating pool of monocytes adherent to the vessel wall is roughly 3 times larger than the circulating pool.
Monocytes and macrophages bridge the gap between innate and adaptive immunity. They actively clear cellular debris, foreign matter, and necrotic tissue through phagocytosis. When stimulated by T lymphocyte signals, activated macrophages ingest and kill complex microorganisms, release inflammatory cytokines, present antigens, and directly attach to and eliminate malignant tumor cells.
Shifting our focus to thrombopoiesis, platelets are anucleate fragments derived from megakaryocyte cytoplasm that orchestrate primary hemostasis. Their normal reference interval in peripheral blood ranges from 150 to 450 times 10 to the third per microliter. In healthy individuals, platelets circulate with a half-life of roughly 7 to 10 days.
Because platelets circulate for up to 10 days, patients scheduled for functional platelet testing must refrain from antiplatelet medications like aspirin for a full 7 to 10 days to ensure uninhibited platelet turnover. Total body platelets are divided into two physical compartments. Two-thirds circulate freely in peripheral blood, while one-third is sequestered in the spleen. Furthermore, immature reticulated platelets containing residual RNA make up 5 to 10% of the circulating count, and an elevated percentage signals increased marrow thrombopoiesis in response to peripheral destruction.
On a standard right-stained smear, mature platelets appear as small, anucleated round or oval structures measuring 2 to 3 micrometers with fine purple granules. However, under rapid turnover conditions or in myeloproliferative neoplasms, you may observe giant platelets exceeding 5 micrometers in diameter, which approach or exceed the size of normal red blood cells.
A critical technical challenge in the hematology laboratory involves EDTA anticoagulant artifacts. In vitro exposure to EDTA can induce platelet satellitism, where platelets adhere to the outer membranes of neutrophils or cause massive platelet clumping. Automated cell counters misinterpret these clumped or satellite platelets as white blood cells, generating a falsely decreased automated platelet count known as pseudo-thrombocytopenia.
To wrap up our discussion, platelets serve as the primary vascular defense against hemorrhage through 4 sequential steps: adhesion, shape change, secretion, and aggregation. Adhesion occurs immediately following vascular injury when subendothelial collagen is exposed, allowing plasma von Willebrand factor, or VWF, to anchor to the exposed vessel wall.
Platelets adhere to this immobilized VWF via their surface receptor glycoprotein 1b under high shear rate conditions. This binding triggers rapid platelet contraction, extending pseudopods, and causing dense and alpha granules to secrete active signaling molecules that recruit passing platelets. Finally, aggregation takes place as plasma fibrinogen forms molecular bridges connecting adjacent platelets by binding to their activated glycoprotein 2b3a surface receptors, creating the primary platelet plug.
Today, we covered the developmental stages, kinetics, and immune rules of monocytes and macrophages, alongside platelet kinetics, morphology, EDTA artifacts, and primary hemostasis mechanics.
Thank you for joining us, and we look forward to having you with us next time.